today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
This is a lab. Measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA, but from many universities and other government labs and organizations. And together, they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The CORUS AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the CORUS AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see, and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to